Today we're going to talk about related rates. So for example, when water is drained out of a conical shaped tank, so we've got some kind of cone shaped tank, looks kind of like this, and we've got some water in here, and that water is draining out the bottom of this thing. The height of the water, okay, which would be here, and the radius of the water, which would be here, and the volume of the water are all related by this formula, V equals pi over 3 times r squared times the height. Okay, so we can differentiate implicitly with respect to t to obtain related rates in the equation. So we would take the derivative with respect to time of the volume and take the derivative with respect to time of this stuff over here. So we get dv dt over here. The pi over 3 kind of, we factor that out because it's a constant. Okay, we use the product rule on the rest of it. So we've got r squared times the derivative of h with respect to t. And then we have h times the derivative of r squared with respect to t, which is 2r dr dt. And then we just kind of simplify things here. Just move the r inside there, or the h inside there. And we have a formula here. Okay, all these different things represent numbers. This is the rate of the height changing with respect to time. This is the rate of the radius changing with respect to time. This is the height, this is the radius. Okay, we've got some constants in here. So all of that is are things that we're going to use in different problems. Okay, so here's an example, two rates that are related. So the variables x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. Find dy dt when x is 1, given that dx dt is 2 when x is 1. Okay, so the first thing we're going to do here is we're going to take our equation, y equals x squared plus 3, and we are going to differentiate both sides with regard to t. Okay, so over here we get dy dt. Over here we get 2x dx dt plus 0. Okay, so now we just fill some stuff in. So what do we have to fill in here? Well, we know that dx dt is 2. So I can take this and I can plug it in here. So I'm going to get 2. I know that x is 1 because it told me that right here. So we can go ahead and plug in 1. 2 is just a constant, dy dt, and that's 2 times 2 times 1, which is 4. So dy dt is 4. And we're done. Okay, so let's look at this example. Ripples in a pond. A pebble is dropped into a calm pond, and it causes ripples in the form of concentric circles. The radius of the outer circle is increasing at a constant rate of 1 foot per second. So if you've thrown a rock into the river, you know that those rings, they're pretty evenly spaced, okay? When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? Okay, so we got to remember a little bit of geometry here. So we've got we got to figure out what our related rate's going to be. And we've got radius and we've got area, so we're going to use the formula area equals pi r squared because it's concentric circles. So we want the rate of the total area, when the radius is 4, what is the rate of the total area A of the disturbed water changing? So we're going to find dA dt. So we're going to do dA dt. It's going to be the derivative with respect to time of pi r squared. Okay, so that's going to be 2 pi r dr dt, because r is not r is not t, so we're finding the derivative of r with respect to t. Okay, so we've taken the different, or we've gotten the, sorry, I'm tongue-tied today. We've differentiated this thing, and what do we know here? We know that the radius, when the radius is 4 feet, so I can take 4 and I can plug that in here for r. So r is 4. Pi is just pi, 2 is just 2. Let's see. And now what are we solving for here? We've got to be careful. Want to make sure we're solving for the right thing. So we also know that the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So that tells me that dr dt, whoops, dr dt is 1, so we're finding dA dt here. And then I just multiply that all out. dA dt comes out to be 8 pi, and that's in square feet per second. You need to get the units down. Okay. So, there we go. 8 pi square feet per second is the area of, as the circles expand at that point in time. Okay, guidelines for solving related rate problems. First of all, identify all the given quantities and quantities that need to be determined. Make a sketch of the thing and label it all the quantities. That is super important that you make a sketch. Okay. Write an equation involving the variables whose rates of change are either given or are to be determined. Make sure to use the chain rule to implicitly differentiate both sides of the equation with respect to time t. After completing step 3, substitute in the resulting equation all the known values for the variables and their rates of change, and then solve for the required rate of change. Okay? So, next up. Okay, so this is just kind of practice for doing that. So the velocity of a car after traveling for 1 hour is 50 miles per hour. Okay, we know that x is the distance traveled. We know that dx dt, that's the rate of change of x with respect to time, is 50 miles per hour when t is 1. Okay. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Okay, V is the volume of water in the pool. Now, if I have a specific geometric shape for that pool, I can use that formula for that geometric shape. We know that dV dt is 10 cubic meters per hour. Okay, that's the rate of the volume of change at time t. A gear is revolving at a rate of 25 revolutions per minute. 1 revolution is 2 pi radians. So, theta is the angle of revolution. D theta dt would be 25 times 2 pi radians per minute. A population of bacteria is increasing at a rate of 2,000 per hour. Okay. X is the number in the population. dx dt would be 2,000 bacteria per hour. All right, let's look at inflating a balloon. So air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Okay, so first of all, we've got a spherical balloon, so we know that the volume is 4/3 pi r cubed. That's the volume formula for a sphere. Okay, other things that we know. We know that 4.5 cubic feet of air is being put in per minute. So that would be the rate of change of volume. So that would be dV dt is 4.5 cubic feet per minute. We know that the radius r is 2. Okay, so let's find the rate of change here. So we're going to take the derivative with respect to time of this whole thing. So I'm going to get dV dt over here. I'm going to get, let's see, 3 times 4/3 is just 4. So this is 4 pi r squared dr dt. All right, so what do I know? Well, I know this goes here, so 4.5 goes there. 4 is just 4, pi is just pi. I know r is 2, so I can put that in here. That's 2 squared dr dt. So obviously I'm going to be finding dr dt. So this is 4 times 4 would be 16 pi. Uh-oh. This would be 16 pi dr dt equals 4.5. And then I just got to divide by 16 pi now. So dr dt is going to be 4.5 divided by 16 pi, which is approximately 0.0895 feet per minute. Okay, so that's the rate that the radius is changing. Now, this is kind of interesting because if you think about what's happening here, oops, I got some stuff down here at the bottom. Let's move this out. The volume of this balloon is increasing at a constant rate. It's 4.5 cubic meters or cubic feet per minute. That's constant, okay? But the rate of change of the radius is not constant. So what's happening is, as the balloon, the radius of the balloon is growing at a smaller and smaller rate as the volume, but the volume is staying the same. So just because you pump in, say you pump in at one point, you pump in 4 cubic feet of air and it makes the radius change by, say, an inch, that doesn't mean that it's always going to change by an inch. That's actually, as it gets bigger, that radius is going to get smaller. So if I pump in another 4.5 later, it's not going to increase an inch. It's going to increase less than that. And if you think about it, it makes sense because the balloon, the volume is getting bigger faster than the radius is. Okay, the speed of an airplane tracked by radar. So an airplane is flying on a flight path that will take it directly over a radar tracking station. The distance S is decreasing at a rate of 400 miles per hour when S is 10 miles. What is the speed of the plane? This is one you're going to want to draw the picture. And I just happened to sketch this little picture here earlier today. Okay, we've got our plane, got a radar station that forms a right triangle right here. Okay, and S is the distance between the plane and the radar station. Okay, so we need to get some stuff down on the paper here. We know that S is also 10 miles. Now, since we know that the height of the plane is 6 miles, we can figure out this up here. We can figure out X by using the Pythagorean theorem. So X squared plus 6 squared is 10 squared. So X squared plus 36 is 100. So X squared is 64, which tells me X is 8 miles. We know that the distance S is decreasing at a rate of 400 miles per hour when S is 10 miles. So we also know that this down here, ds dt, is negative 400 miles per hour. Okay. Now, how are we going to find the speed of the plane? Well, we have a related rate. We know that S squared, so this squared is equal to X squared plus 6 squared. So S squared equals X squared plus 36. Okay, now we're going to take the derivative of this. So, with respect to time, okay, so we're going to get 2s ds dt is going to equal 2x dx dt plus 0. Now we know x. X was 8. So we can go ahead and substitute that in there. The 2 is just a constant. 2 is a constant here. Okay, what else do we know? We know S. S is 10. Okay, so this is going to go right there. We know ds dt. That's going to be negative 400. So this is going to equal that equation right there. Now we just have to solve it. So let's see, this is negative 400, negative 4,000, negative 8,000 equals 16 dx dt. So dx dt is negative 8,000 divided by 16, which is negative 500 miles per hour. That's the actual speed of the plane. Now, don't get speed and velocity mixed up. Oh, and speed would be the absolute value of the velocity. This would actually be the velocity, so that'd be 500 miles per hour. Okay, changing angle of elevation. This is one of the tougher ones here. Find the rate of change in the angle of elevation of a camera at 10 seconds after liftoff. Okay, here's something you need to make sure that you do in these problems. A lot of times the problem does not give you all the information. They'll have a picture, so they got a picture similar to this, and they'll have other information down here in the caption to the picture. And that's the case on this particular one. If you're looking in the example, there's not enough information in the problem to solve the problem. Okay, so we do know this is 2,000 feet because it tells us down here the camera's 2,000 feet from the launch pad. We know the camera's at ground level, filming the liftoff. It is rising vertically according to the position equation. S equals 50t squared. Well, this is S right here. So this is also 50t squared. So what's happening is as the time increases, this goes faster and faster. S gets bigger and bigger. Okay. Now, we need to figure out a related rate, and the only thing we don't really know here with this right triangle is we don't know what x is, okay? But we do know this. We know that the tangent is s over 2,000 because the tangent is the opposite over the adjacent, okay? So our related rate that we're going to use is going to be tangent theta is going to be 1 over 2,000 times s. That's the same as this. Okay, so we're going to take the derivative. So the derivative of tangent is secant squared d theta dt. And this is going to be 1 over 2,000 ds dt. Okay. Now, what do I know here? Well, let's see. I know that ds dt, I can figure out that too. ds dt, I have s here, so I can figure out ds dt. That's going to be 100t. That's just the derivative of s with respect to t. So I can go ahead and plug this in here. So this is going to be 100t. This is a constant, so it's going to stay 1 over 2,000. Let's see. I'm trying to figure out, what am I trying to figure out here? D theta dt. So let's just go with this. We'll just substitute that in here. Secant squared theta d theta dt. Okay, so this is 100 over 100t over 2,000. So that's going to be t over 20 is going to equal secant squared theta d theta dt. Okay. Oh, and I know t. T is 10 seconds because it tells me that right there. So I can go ahead and put a 10 in here. So this is 10 over 20, which is 1/2. So secant squared theta d theta dt is 1/2. Now I want to figure out what d theta dt is. So I'm going to divide both sides over here by secant squared theta. And so I get d theta dt is 1/2 times 1 over secant squared, which is just cosine. So d theta dt is 1/2 cosine squared theta. Okay, so Oh, cosine. So we got to figure out what cosine is. So the cosine would be the adjacent over the hypotenuse, which we don't know what the hypotenuse is yet. So we're going to use the Pythagorean theorem to figure that out. So let's see here. S squared plus 2,000 squared is going to equal x squared. And then x is going to be the square root of s squared plus 2,000 squared. That's going to be this. So let's see. The cosine, let's see if this is square root of s squared plus 2,000 squared, then the cosine is the adjacent over the hypotenuse. So here we go. This is going to be, the adjacent is 2,000, and the hypotenuse is going to be the square root of s squared plus 2,000 squared. And then this is going to be the cosine squared times 1/2 is going to be d theta dt. Now I know that s is 10 because it tells me that right here, s is 10. So 10 seconds, yep. So I'm going to go ahead and substitute 10 in here. And then I just calculate it. So d theta dt, I'm going to need a calculator for this one. So that's going to be 0.5 times, in parentheses, 2,000 squared divided by the square root of 10 squared plus 2,000 squared. And then that is going to be squared also. I got to go back and put a parentheses in there. And of course, I'm having trouble getting this put into the calculator correctly. There we go. Boom. Comes out to be 0.499. That's a hat? No, that's not right. Okay, we need one more number to figure this out, and we need to know what S is. Okay, so we can go up here to S. S is 50 times t squared, and we know that t is 10, so this would be 10 squared times, so we'll say S of 10 would be 50 times 10 squared, which would be 50 times 100, which would be 5,000. So S is going to be 5,000. So we're going to go ahead and put in 5,000 squared here. Okay, and now we can calculate it. So 5,000 squared plus 2,000 squared is a big number. We're going to square root that. And then we're going to take 2,000 and divide it by that. And then we're going to square that times 0.5. Comes out to be 0.06896. And that should be in what, radians per second, probably. Yep, radians per second. If you did it in a fraction, that comes out to 2/29ths. So you could have that too. Either one of those will do. Remember, if you're on an AP test, always take things out to at least 4 decimal places. And there you have it. So here you go. Go ahead and do those problems. There's not a whole lot of them there, but they do take a little bit of time, and I will see you next class.